Hello, welcome back. We're going to look at asymptotic notation. So what we have been discussing is a way to measure the running time of an algorithm. And we saw that this measure of the time complexity of the algorithm should not be depending on the software or the compiler or the hardware being used. It should only depend on two factors: the complexity of the algorithm you have written and the input size. Right. Now, therefore, we have seen that this is the kind of idea we would want. We would want to say that the algorithm takes time proportional to n square, where n is the input size, or the algorithm takes time proportional to n, where n is the input size. So these are the kind of statements we would like to make. And also, we also mentioned the following fact that whenever I talk about the running time or time complexity of an algorithm, I am talking about the worst case running time. We also saw that there can be three analysis, three way you can analyze: the best case running time, the average case running time, and the worst case running time. The best case is not really good as an analysis tool. The average case is good, but it's very too complicated to analyze. And the worst case is therefore used as a tool to analyze algorithms. And so when I am saying that the running time of an algorithm is proportional to n square, I mean the worst case running time of the algorithm is proportional to n square. Okay. Right. Now, this is clear. So we want a notation which can forget about these constants. Now, another fact we would like to want is, let's see an example, and you should tell me. Let's see an example. So we have two algorithms. Let's say A and B. Okay, and I want to compare the running time of these two algorithms. And so this is you can just assume this is A of n, and B of n is the running time of these algorithms. So these are two algorithms, running time A of n and B of n on when an input of size n is given. And I'm going to plot the graphs of this A of n and B of n, and then you should tell me which is a better algorithm. Okay, right. This one. Okay, so this is and okay. Now, as can you see the plot? So this on the x-axis it is the size of the input n, and on the y-axis the worst case running time for the algorithms A and B. And as you could see, A of n takes more time than B of n at the initial stages, and then after that B of n takes more time. Okay, on any inputs after this point, B of n takes more time. Okay. Now in this scenario, which is the better algorithm? Should I go for A or should I go for B? Right, this is what what should we prefer? Okay. Now, obviously, it all depends on the kind of input you get. If your input is going to be only here, it's better to go for B of n. But one thing which we have been telling is, always think that we are writing your program, your coding for huge input, large input. Okay, the programs you write are for large input. So therefore, our analysis is also going to be let's say skewed for large input. So we are analyzing to say that when is an algorithm better than the other when you are getting large input. Okay, so since this is the kind of philosophy with which we are working, we prefer, in these two cases, we would prefer this as the better algorithm. This takes lesser time compared to this is time. Okay, So this takes lesser time. A of n takes lesser time on an size n input than the algorithm B, right? So this is better. Okay, and this is the preferred thing. So this point is kind of the point which we will, let me call it n0. Okay, why am I marking this as n0? We'll soon see. Okay. So this is the kind of the philosophy with which we are going to work, that given two algorithms like this, if B of n is going to take more time after a point, B of n is going to take more time for like after this point in n0, then B of n is considered to be worse than A of n. Okay. So these are two notions which we have talked about two notions now, and the tool for our analysis should um, basically take into consideration these two notions, right? So notion number one is the fact that we should be able to write that this algorithm is proportional to n square, where n is the input size, and the second notion is that the algorithm should be talking about large input, not small input. These are the two notions which we would want to talk about. Okay, like we would want to use in our comparisons of algorithms, right? And this brings us to our first notation which we would be interested in is called as the big O notation. Okay, or it's written just as like this, an O, or it's called as a big O notation. And why is it big O? You will soon see a small O notation after some time. Okay. Let me try to let me explain this big O notation. Okay. So we say that the running time of an algorithm, so this is the running time of an algorithm T of n. It takes T of n time given an input of size n. The worst case running time of an algorithm which takes an input of size n. We say this is equal to O of n square, okay, or it's you can we will even tell it as order n square, okay. Okay, so this is how we might be saying T of n is equal to order n square, O of n square, etc. These are the kind of phrases we will be using. Okay, so T of n is equal to order n square if, so we say that the time running time of an algorithm is order n square if okay, if the following happens. If there exist two constants, okay, so C and n0. Okay, so these are constants which are greater than, let's say, greater than 1 or greater than or equal to 1. So there are two constants C and n0 such that you have to see this fact, I mean see this carefully. So two constants C and n0 such that, so okay, oh, sorry, this means there exist there exists C n0 greater than or equal to 1 such that for all I will rub this thing off so that it's, so we say T of n is equal to big O of n square if there exists C n0 such greater than or equal to 1 such that for all n which is greater than or equal to n0 the following is true. Okay. And what is the following? The following statement is that what am I saying? If n is greater than or equal to n0, then T of n should be less than or equal to C times n square. Okay, so this is C n square. Okay, so right, so C is a constant, so C n square. This is what you are saying. T of n is equal to big O of n square if there exists C n0 greater than or equal to 1 such that for all n greater than or equal to n0, the for T of n is less than or equal to C n square. This is our claim. And I could have written anything here. Okay, so this could have been n. If this was n, this would be T of n is less than or equal to Cn. I could have written this is n cube, then T of n is less than or equal to Cn cube. Right? I could have written here 2 raised to n, then T of n is less than or equal to C2 raised to n. Okay, I could have written here log n, then this would have been C times log n. So this is whatever is here, it's basically here. So this is f of n, and this also is f of n. Okay, so T of n is equal to big O of f of n if T of n is less than or equal to C f of n, provided there are constants C and n0 such that all these things happen. This is the definition. Okay, now we look at a few examples to understand this definition. Let me do some examples. Let me work out some examples here. Okay, so I'm going to work out a few examples. I'm going to write T of n. Let me say T of n is equal to I don't know, 10 times n plus 5. Okay, this is my T of n. Then I can write T of n is equal to O of n. Okay. Why is this true? Now to do this, to prove this, what is it I have to do? So I'm saying, let's assume, I have T of n is equal to 10 n plus 5. Then it means T of n is equal to O of n. Okay, so if I have to show that T of n is equal to O of n, what does it mean? I have to show that there exist two constants C and n0 such that for all n greater than that n0, T of n is less than or equal to C times n. Okay, so this here it is n. Right? This is what we are interested in. Okay. What are the two constants? What is the constant I am going to pick? So I can let me just state something. I'm going to choose my n0 to be. This is some. I mean, there might be better constants, but I'm going to choose constants so that you can prove this fact very easily. I'm going to choose constants. So the constants I'm going to choose are the following. Pick C to be, let's say, 11 and n0 to be, let's say, 5. Okay, these are my constants I have taken, 11 and 5. And then what is it I have to do? I'm going to show the following, right? For all n, so I have 11 and 5, and then I'm going to say that for all so the proof of this is the following. Proof for all n greater than or equal to 5, right? Greater than or equal to 5, 10n plus 5 is less than or equal to, see, constant is 11 times n. Is this true? Let me see. This is true because you bring 10 to this side, it becomes n is greater than or equal to 5, right? Okay. So this is true. So what you have just now argued is that, so this is the proof. Since for all n, um, 10n plus 5 is less than or equal to 11n, you are done. So what I just now argued is that if you take these constants c and n0, 10n plus 5 is less than or equal to 11n, and therefore t of n is equal to big O of n, right? We're going to go through a lot of examples now, and you have to get familiarized with this notation. And we'll go through a lot of notation so that you get comfortable with this notation, and you can also work out a lot of examples in your own, by your own, okay?